So hello those on the recording. Actually, really? Hello, I'm David, in the case you've never seen me, because people complain that they've never seen my voice, or at least I see them in the Maths Learning Centre and say, oh, your voice is really familiar. You're the guy who does revision seminars, aren't you? So now you see my face, so you know who I am. Okay. Right, so do some multivariable calculus. I'm not going to do all of it. It's quite a lot of it that's already on the Maths Learning Centre's website. And so the specific thing I was asked for most, well, when I say most, by 2 or 3 people, was to talk about the multivariable chain rule, but I was also asked to talk again about the geometric interpretation of gradient and that sort of thing. So I'm going to start with the multivariable chain rule so that you can see how I do it. And that is something that's missing in one of the videos, that the recording stopped there. So multivariable calculus, the chain rule. So when you first learn the chain rule, at least in maths, you probably learned it. That's a bit better. You probably learned it in the terms of this. So you probably learned it like this, where you had like, you know, some function was f of g of x. And then when you differentiated it, you did the outside. But you also had to multiply by the derivative of the inside. And that's probably what you did when you did one variable. But multivariable calculus is a bit trickier, and the dash is a bit difficult to understand which variable it's referring to. And so what we do is we need to use the other version of the one variable chain rule. So the other version of the one variable chain rule is that you've got a function, maybe y, which is a function of u, which is a function of x. And then you go that dy on dx is dy on du times du on dx. This is Leibniz's version of the chain rule. And that's the one that's used a lot in physics. You know, people use that in physics heaps, and there's this classic thing that you do in dynamics where you use the chain rule and you magically get this thing that has v and dx and stuff in it. It's a very fancy trick. This is the version that we need to use to be able to do this in multivariable. I'm just going to draw a picture of how this works, just to give you something that helps me remember how the multivariable chain rule works. So this is my picture in the one variable case. So you've got an x, that would be your x-axis on a graph, or a graph if you like, and every value of x is being plugged into a formula to produce a value of u. And then each value of u is being plugged into a formula to produce a value of y. And so I have this value of x, maybe it's 3, chuck it into some formula and it gives me a value of u, chuck it into a new formula, it gives me a value of y. Okay? That's the concept that I have going on here, that I have functions nested inside each other and each one is producing a new value. And then you can pick another value of x and it would go to some other value of u, which would go to some other value of y. And as you move this point back and forth, it will move this point back and forth, which will also move this point back and forth. And so we can think about moving this along in time and watching what happens to u and y. And that's the really important thing that we're thinking of here, because that helps me understand how the chain rule works. Sharpen a different coloured pencil. So the idea is that we're going to have this particular value of x that we're at, and we're going to move by a little bit. And that little bit is called dx. And me moving the dx by a little bit is going to cause u to move a little bit as well. And that's du. And maybe du is a bit bigger than dx. But then moving the u is going to cause y to move a little bit. And that'll be dy. And the idea of the differentiation is that you're going to make a model of how this change works and to say that du is some multiple of dx and dy is some multiple of du. And so the multiple that you multiply dx by to get du is called du on dx, because that's how you'd figure out how to multiply. If I wanted to know what I had to multiply 5 by to get 20, I'd go 20 divided by 5. So that's what I'm going to do. So this is called du on dx here. And this is dy on du. And so what I end up with is dy is dy on du times du, but du is du on dx times dx, and then I divide both sides by dx and it all works. See, now I've divided both sides by dx and I get dy on dx is dy on du times du on dx. Now I'm probably being ever so slightly dodgy here with the whole let's divide by dx and suddenly it's a derivative. It's not technically a fraction, but to all intents and purposes, for almost all situations, it actually is. So we're going to believe that that's how it works. So just remember that at this stage here, this fraction is representing a single number which multiplies by du to get the dy, but then we can also figure out what a number is by dividing to see what that number is. Okay, that's the one variable chain rule. Right. In two variables, or multiple variables, it gets a bit crazier. Okay, here we go. With two variables, it may be, put a heading, with two variables, perhaps you have z being a function of both x and y. Okay, so here we have, leave a bit of space, I'm going to draw something up here. Here we have x, and here we separately we have a y as well. And both of those things have an effect on the z. Okay, so together a value of x and a value of y together produce a value of z. So let's think about this. We might move the x by this much and move the y by this much. And the idea that we're going on is that this change in x will, if I kept the y as it was, this change in x would cause a little change in z. And if I kept the x the same, the y would cause a little change in z as well. And together, those two changes are the change in z. Okay? I'm just going to recolour this one. That's the one that goes with y, with x, the orange one. And this is the one that goes with y, green one. Okay, so this change here, this orange one, is going to be just like it was before, a multiple of the dx. So what I'm going to get is that my change in z is going to be something times dx plus something times dy. So this is this little arrow here. So this is my second orange arrow. That's what this is. This is my second green arrow. And together they make up the big dz. The name of this number here, back in one variable calculus, that would be dz on dx. When two variable calculus, it's still called dz on dx. So just we use a curly d to point out that there's only one variable involved here. So what we're multiplying by to get from here to here is timesing by dz on dx, and to get from here to here we're timesing by dz on dy. Sorry about that. This is how I remember the chain rule. It says the change in z is made up by a little bit of change that's caused by the change in x, and another little bit of change that's caused by the change in y. Okay, so that those two, the x and the y, separately cause their own changes, and together that adds up to the change in x, in z. All right, now here's what I add to the picture. What if the x and the y weren't just moving independently as I wanted them? What if they were both being caused to change by another variable? What if there was a variable t that dictated the change in x and dictated what x and y were, and there was a little change in t? Okay, my goal now is to say, well, what if I could hopefully ignore everything that happened in the middle and directly figure out how dt is related to dz? Well, I would first need to know how dt changed the dx, and that would be dx on dt, and how dt changed the dy, that would be dy on dt. Right? And so I would say that this dx was really dx on dt times dt. And this dy was really dy on dt times dt. And now I know how dz is related to dt, because I could just divide both sides by dt now and get that. Of course, if you were really thinking clearly, you could have just divided that one by dt. If you divide the dz and the dx and the dy by dt, suddenly it's this. So that is my understanding of it. I don't know if it will help you, but if it does, I'm very happy that it does. If it doesn't, well, I can talk to you in the Maths Learning Centre and we can come up with something else. Okay? So my understanding of two variables, that's my complete understanding of, well, not the complete understanding, but my complete picture of how it works. I have this picture of different variables acting on other variables. But I have yet another way of understanding this that doesn't take so long, which allows me to do exams quicker. So I'll show you that too. And it goes like this. So another picture is that I imagine that my z, and I draw it up the other way, I imagine that my z has an x and a y which are causing it to change, and that my x is caused to change by a t and my y is caused to change by a t as well. You could imagine that I could have, like I did before, the two branches coming from the t, but I find this version easier because it ramps up to the multivariable chain rule a little easier. So in my head, I go, well, in order to achieve dz on dt, I work my way down these branches. So I have dz on dx and dx on dt. And then I also have dz on dy and dy on dt. Which is why I draw it up the way I do, because then the z is on top of the y as it is in my fraction here. And that is the chain rule, basically. I will do an actual example with actual functions in a minute. What about this picture? Now, z is a function of x and y, but x and y are both functions of both u and v. It's all good because I just have to follow the paths in my tree diagram. There it is. So now let's look. Suppose I wanted to know dz on du. When I look at this diagram, at the bottom there's two variables, so it's going to be curly z on curly u, because the z is related to two variables at the bottom. So let's see. dz on du. Cool. So I find all the branches that end in u. There's one here, and there's one here. So, coming down this branch, I have dz on dx, and then the next branch down is dx on du, and that's a curly because there's two possible paths to choose from here. And then I have to go down this branch, so dz on dy and dy on du. So you can imagine that this could get really complicated. Well, it could look really complicated. It's not actually as bad as it looks because the tree diagram always works no matter how many variables are involved and no matter how many layers there are down. Okay, so I could, you won't get one like this in the exam, but it's not like you couldn't do it now because I could have z being a function of x and y and t, and x is a function of u and v, and y is only a function of v, and t is a function of u and v. And I could go another layer down if I really wanted, but I won't. Sorry. And then, so that's what I've got here. X is a function of y, and x and y and t. Sorry, z is a function of x and y and t. X is a function of u and v. Y is a function of just v. T is a function of u and v. So let's see what dz on dv is. So I have three paths that end in a v. This one, and this one, and this one. So it'll be dz on dx, dx on dv, plus dz on dy. Now there's only one choice of variable here, so it'll be a straight d. Sorry, it's a b. And then there's another path here, dz on dt, dt on dv. So because there's three paths that end in a v, there are three pieces that are added together. And the difference between a straight and a curly is how many choices there are at each path. There's only one choice of where to go, so it's a straight D, but all the other ones have more than one choice, so it's curly. All right, that's the chain rule. Let's do a proper example. Yeah. So there are at least a couple of different examples you could be given, depending on how they give you your information. And I'm not sure if I can do both of them, but if you've got one that I don't do, feel free to sing out and say, could you do this example in a second? So here's an example. Let's do that one. So z is equal to x squared plus 2xy plus y e to the x. And yep, that'll work. Cool. And suppose I'm asked to find dz on dt at the point where t is 0. Chose a nice easy point. Okay, so that means I'll draw my diagram and it will tell me what to do. So my diagram goes that z is a function of x and y, and they are both functions of t. And so dz on dt, because there's only one variable down the bottom, it's straight, is dz on dx, and then dx on dt, plus dz on dy, and then dy on dt. So that's my formula that I'm going to need to use. So in order to figure out what dz on dt is at this spot, That's an equal sign. I'm going to need to figure out dz on dx, and dx on dt, and dz on dy, and dy on dt. Now, it is not necessary to sub in all my variables, okay, and get it all in terms of t. I could do that. I could sub in sine t instead of x and t squared plus 1 instead of y, and just differentiate it as I normally would, and that would work perfectly well, okay? But I'm trying to use the chain rule to do this, so I'm illustrating it using the chain rule. Okay. So, I need to figure out what all of those pieces are. So I'm going to start with dx on dt and dy on dt. So x was equal to sine t. I might start it on this new page. X equals sine t. So dx on dt is cos t. Cool bananas. And y is t squared plus 1. So dy on dt is 2t. Cool. And that means that when t is equal to 0, so at t equals 0, I get dx on dt is cos of 0, which is 1, and dy on dt is 2 times 0, which is 0. Lovely. Okay, so the next thing I need is dz on dx and dz on dy. So we've got z was equal to x squared plus 2xy plus y e to the x. So let's see, dz on dx. So that means that in a purely variable algebra sort of way, we're going to treat y as if it was a constant, and the x is my variable. So all those y's could just as easily be replaced with 7 or 13 or 2000, and I could do my derivative and then find those numbers and replace the y back with them if I wanted. Or I can just think carefully of what's going on. So this variable, that's just x squared, and I can differentiate that with respect to x. That'll give me a 2x. This one here, the y counts as a constant. So constants that are multiplied on will still be there after you differentiate, so it'll still be there, and then the derivative of 2x is 2. This y counts as a constant, so it will still be, and it's multiplied on, so it'll still be there afterwards, and the derivative of e to the x is e to the x. So that's dz on dx. So 2x plus 2y plus y e to the x. Okay. And I need to figure out what that is when t is 0. Okay, just a second. When at t equals 0, so in order to figure out what dz on dx is, I'm going to need to know what x and y are. So x equals sine t, so it'll be sine of 0, which is 0. Y equals t squared plus 1, so 0 squared plus 1, which is 1. And then I sub them both into there, so dz on dx comes out to 2 times 0 plus 2 times 1 plus 1 times e to the 0, which is 2 plus e to 0 is 1, which is 3. Great. Always nice when it works out to be a whole number and not something involving e. Okay. I'm just going to start with the z again so that you can see it on the page. So now I need dz on dy. So let's think. Now, because it's dy, the x counts as a constant, so I'm going to have to go, right, x squared does not involve a y at all, so this counts as a constant, so when I differentiate it, it will disappear. 2x is a constant and it's multiplied on, so I'll get 2x, and the derivative of y is 1, so cool, that's tx. E to the x counts as a constant and it's multiplied on, so it'll still be there, and the derivative of y is 1. So that's what I get for dz on dy. So at t equals 0, We know that x was 0, we already figured that out, and y was 1. And so dz on dy is going to be 2 times 0 plus e to the 0, which is 1. Okay, we now have all the pieces we need to calculate what we were looking for. So dz on dt was dz on dx times dx on dt, and separately dz on dy times dy on dt. And let's go looking. dz on dx was 3. dz on dx on dt was 1. dz on dy is, we just figured that out, is 1. And dy on dt was 0. So we get 3. In a purely technical sense, they would be most impressed if you said this. dz on dt evaluated at the point where t is 0. Okay. So to be completely honest, once I found out that dy on dt was 0, it wasn't worth figuring out dz on dy because it's going to be times 0 anyway. But for completeness' sake, it's good to do all of it. That's using the chain rule like that. And you can imagine a question where they didn't give you any of the formulas and they just told you what all those numbers were. Okay, they just told you what dz on dx worked out to be and what dz on dy worked out to be. Or you can imagine a question where instead of being told that x was sine t and y was t squared plus 1, all you're told is the value of x when t is 0 and the value of x dashed when t is 0. So that you're not told what the formula is, you're just told what the answers are for the derivatives and the original function. So that would mean that you wouldn't have to do any of this bit of the working here because you'd have those answers already. Classic thing that they do in exams and assignment questions is to give you some of the information. So at any point if you go, well, what would I do if I knew all the information? And then see if the bits of information you've got fit into those gaps. That's the multivariable chain rule. Now, before I move on to anything else, do you have any questions on that? Yep? So the question for the video was, is it acceptable in maths to use dy dt as y dot? Well, I've never seen your lecturers use it, so I would say don't. But it is actually acceptable. Like when Newton, invented calculus, he used dashed for the derivative with respect to x and dot with the derivative with respect to t. You could at least you could if you wanted to put a note, I represent derivative with respect to t as a dot, if you really want to. The people who are reading it will cope, but I do feel that it's probably safer to just do the ddt thing, at least in this exam. Future, do whatever the hell you want, as long as you're clear on what your notation is. Yes. There's actually no particular reason why the dash has to represent derivative with respect to anything. So you're supposed to tell people what it means every time, but it's been around for long enough that people are okay. But over in dynamics, it gets quite confusing when you've got both of them. Okay. Well, the only other thing was a quick description of, sorry, I'm just trying to look at the time. And I think that Tracy's going to want to use this lecture theatre. Just give me a second. Have you got something in here? All right, we've got about 10 minutes before we have to find another room. As I warned you about the international students. So about 400 of them will be wanting to come in here shortly. Look, we will be leaving very soon. So people have asked me about the instinct, what's the geometric interpretation of the gradient and directional derivative and the discriminant. Do watch David's, your lecturer's lecture from last week if you didn't go to it. He did a fairly good job with my models, and my revision lecture that's already there talks about that too. But I do want to talk about the discriminant, the second derivative test, because it just gets confusing for a lot of people. So I just want to mention some stuff. So there are 4 second derivatives, okay? So when you take a function that's a function of 2 variables, an x and a y, you can do the 2 original partial derivatives. But then those themselves are functions which can be differentiated again, and they're usually functions of both x and y again. So you can differentiate them both with respect to the 2 variables. So you can imagine doing d on dx of this d on dx of dz on dx, which gives you d squared z on dx squared. I mean, that's the literal notation. D times d is d squared and dx times dx is dx squared. It's fairly scrappy, but that's how they do it. And then you could do d on dy of dz on dx, which would be d squared z on dy dx. Okay. So, and you could do it with the dz on dy as well. So you'll notice that in a completely technical sense, the dy dx on the bottom means you've actually done the dx first and then the dy. But it doesn't actually matter which order you do it in, it'll come out to the same answer every time. And we also write this notation as f, and then you differentiate it with respect to x, and then you differentiate it with respect to y, and then you go fxx and fxy and fyx and fyy. This time the yx means the y has been done first and then the x, because of where it is in relation to the function that it's being differentiated. Okay, so you see the y is next to the f, so it's done first, whereas in this one, this y this dx is actually next to the z first. So, not that that's very important. The second derivative test says you need to figure out all 4 of those derivatives at the point you're interested in and figure out a determinant. Possibly the other way around, doesn't matter. So the idea is that if this comes out as positive, then that means it's upwards curvature in every direction. Okay? And that is, or possibly negative downwards curvature in every direction. We can't tell which one it is. So then there's 2 things. If xx comes out as positive, then it's a minimum. If fyxx or yy, doesn't matter which one, comes out as negative, then it's a maximum. And that's because this fxx is the curvature in the x direction. So just like with ordinary functions, if you get a second derivative being negative, it's a maximum. If this comes out to be negative, it's what they call a saddle point. And if this comes out to 0, you have no idea. The test fails because it doesn't tell you anything. So, down a bit. Right, here we are. This function here we go. At this point here, that's the top of a hill. it's curving downwards no matter which direction you face, that will mean that that discriminant will come out as positive. Okay, because both xx and yy are both negative, so the determinant will come out as a plus. So that's a local maximum. This is a local maximum here as well. There's a local minimum at the bottom of this valley, and that's where the discriminant comes out as positive still, but when you look at the individual fyy and fxx, we get positive curvature. So that determinant comes out as positive, but the individual entries come out as positive too. And this point here, it's a maximum if I go around this way, but it's a minimum if I go this way. And that's what a saddle point is. And so you'll end up with the determinant of that matrix coming out as negative. I'm going to stop there and let these guys in. And